Welcome back, guys. I apologize for having to break this video up, but my smartboard has been acting strange. So I'm just going to pick up where I left off on the Algebra 2 Quarter 4 review packet. You'll notice in the last example, number 6, I've actually changed the equation to be x squared minus 2x minus 3 over x squared minus 1. And I did that because I think you need to see what the original function looks like when both expressions are in standard form. Because when we're graphing rational functions and they're like this, the first step is to factor. And so I had originally provided an example that was already in factored form, but I think it's important to see what the original function might look like. So if I take a look at this situation, what I want to do is I want to write the numerator and denominator in factored form. So if I take a look at the numerator, that's a trinomial. We're going to use a process, where we try to find the product of two numbers that'll give me negative 3. So I'm looking for two numbers that are going to multiply to give me negative 3 and add to give me negative 2. And so I can figure them out to be negative 3 and positive 1. So when I factor my numerator, I'm going to have an x minus 3 and an x plus 1. And in my denominator, if you recognize, that's just the difference of squares. So I'm looking at the root for both x squared and 1. And so I'm going to have x minus 1 times x plus 1. Sorry, my board is probably just going to keep doing this throughout the video. So just bear with me, please. Okay, so once I have it in factored form, remember if we have a pair of factors that cancel, so if I have the same factor on top that I have on the bottom, that's going to be associated with a hole in the graph. So to figure out the hole in the graph, I'm going to set that x plus 1 factor equal to 0. And if I subtract 1 from both sides, I find that x equals negative 1 is going to be a hole in the graph. So when I go to graph my function, wherever the function looks like, wherever the point is associated with x equals negative 1, I'm actually going to make it an open circle because the function won't be able to exist there, because that will generate a 0 in the denominator. Okay, the other 0 in the denominator would occur with this factor here, this x minus 1, and that's going to give me my vertical asymptote. Because wherever the denominator is 0, the function can't exist, because I cannot divide by 0. So the other expression on the bottom is going to correspond to an actual asymptote. And the reason there's a difference, the function keeps continuing in the same pattern that it was, but with an asymptote, the graph sort of approaches it like a limit. So it gets closer and closer and closer to that line without ever really touching it or crossing it. So if I set this quantity, x minus 1 equal to 0, and I solve for x, here we go, I will find that x equals 1 is my vertical asymptote, and I believe that goes here. Okay, so once I know where my vertical asymptote is, I can go ahead and draw that line here. The horizontal asymptote I find by comparing the degree of my original problem. So if I look at the numerator, it's got a degree of 2. The denominator also has a degree of 2. And remember, the degree of a polynomial is just the highest exponent. When the degrees are the same, my horizontal asymptote is found by taking the ratio of the coefficients. So if I think about the coefficient of x squared in both cases, it's just 1. So that means my horizontal asymptote is going to be 1 over 1, which is just 1. And that goes here. Oops. Just bear with me. So y equals 1. All right, so remember the horizontal asymptote is going to go horizontally. So it's going to look like this. Okay, so the next thing I need to do is figure out what the rest of this graph is going to look like. And if this were in the non-calculator section, you couldn't just plug it into the calculator and look at the pattern. You'd actually have to plot some points. So I know that I have a hole at negative, I plotted my vertical asymptote in the wrong spot. Let me fix that. I plotted my vertical asymptote where there should be a hole. I apologize. So here's where my vertical asymptote should be. here's where my horizontal asymptote should be. My whole is what occurs at -2. I just don't know where to put that yet because I'm not sure which part, like if I'm dividing this graph into quadrants, I don't know which quadrant my graph is going to actually appear. So I'm going to go back to my original equation, and I'm going to create a little table of values. For x and y. Okay, so I want to pick values of x. I want to pick a couple that are below the whole, a couple that are between the whole and the x or vertical asymptote, and then a couple on the other side. So I'm going to pick a couple that are low. So I'm going to go ahead and do, like, I don't know, maybe -5. I can do -2. I'll do 0. 2, 3, and 5. Now, I am not going to take the time to go through all of the math with this. I'll do it for 1 or 2, and then I'm just going to fill in the values so that we can move forward. But if I were to substitute a -5 into my equation, I'm going to end up with, and I'm going to put this in parentheses. Shoot. All right, -5 squared is 25. If I take, because I'm just basically plugging the -5 in for x, when I plug in the -5 for this x, -2 times -5 is going to give me a +10. Then I have -3. All of that is going to go over -5 squared, again, is 25 minus 1. So when I simplify that, I actually get about a 1.3. When I plug in -2, I'm going to get a 1.7. If I plug in 0, I get 3. 2 is -1. If I plug in 3, that's actually going to be my intercept. And if I plug in 5, I get 1/2, or 0.5. So if I start to graph these, at -5, my point is going to be at about 1.3, which is going to be about right here. At -2, I'm going to have a point at 1.7. It's going to be about right here. At 0, I'll be at 3. So you can see now that this graph is going to be a curve that kind of increases. So I'm just going to kind of sketch it right here. It's going to increase toward that vertical asymptote. The only thing I have to remember is that I have a hole at -1. And so what I want to do is find out where x equals -1, and I want to make sure that I really define that hole. So it's really obvious that I have a hole there. And then I'm going to go ahead and plug in the values on the other side of my horizontal or my vertical asymptote. So at +2, I have a point at -1. At 3, it's 0. So right now I can see that this side of the graph is going to look like this. When it comes to the domain, I need to remember that x is not allowed to equal -1 or +1. So when I write my domain, it's going to be in 3 different parts. So anytime you have a hole, your domain is being broken up into 3 parts. It's going to go from -infinity to -1, from -1 to +1, and then from 1 to infinity. And notice that I have the curved brackets for each one of these intervals, and it's the union of each. You will not have to do this for the range. But if I were to plug in the value of -1 into what's left of my equation, I'm going to end up with -4 over -2, which reduces to 2. So this value here, where my hole is, occurs at -1, +2. That's where my hole is. But that also gives me the value of y. So y is not allowed to equal 1. That's my horizontal asymptote. Or 2, because that's where the hole is. But like I said, you're not going to have to know that for your quarterly. So when I'm jotting down the intervals for my range, it's going to go from -infinity to 1, from 1 to 2, and from 2 to +infinity. So you just recognize that it's in 3 little sections. Okay, let's move on to the next section. This is where you're simplifying rational expressions, or adding, subtracting, multiplying, and dividing. In this section, it is absolutely imperative that you are able to factor. And so I've attached, I'm going to go ahead and flip to the next page, I've attached a flow chart that I use with my students to help them factor. And one of the things you always want to look for first, and a lot of times people forget to do this, is to see if there's something in common that you can undistribute, that you can factor out or undistribute. Because that will simplify the expression. The next thing you want to do is count the number of terms. So you want to look for a binomial, which means that there's 2 terms left in the expression. A trinomial means that there are 3 terms. And the only other binomial that you might look, or the only other polynomial that you might look at, will have 4 terms. And so if there's 2 terms, there's really only 2 patterns. You're either dealing with perfect squares or perfect cubes. And that's a really obvious thing, because you're either going to have x to the 2nd power or you're going to have x to the 3rd power. And then you have formulas that follow. If it's 2 perfect squares, you're going to follow the difference of squares pattern. So for example, here it's a squared minus b squared. And basically what you're going to do is take the root of each and then multiply the difference times the sum. So for example, if you have x squared minus 4, those are both perfect squares. I'm going to take the square root of each. So that's going to be x and 2. X and 2. One of those parentheses is going to be addition. One of them is going to be subtraction. And I'm done. When it comes to perfect cubes, and actually notice that the sum of perfect squares can't be factored. It would be something considered prime. But with differences, or with perfect cubes, I can look at the difference or the sum. So let's just go ahead and do an example if I've got perfect cubes. So let's say I have x cubed minus 27. I need to take the root of each, the cube root of each expression. That's going to go in my first set of parentheses. So the cube root of x cubed is just x. The cube root of 27 is 3. In the first set of parentheses, I'm going to follow whatever the sign is in that expression. So if it's x cubed minus 27, this is going to be x minus 3. So in the next set, it's going to be a trinomial. And the first and the last term now are just the perfect squares of those terms. So I'm going to have my x squared. Sorry, my board's not calibrated again. Let me just undo this a little bit. Okay, so I'm going to have the square of both of those. So I'm going to have an x squared and a positive 9. So those 2 expressions will always be positive. The middle expression is just going to happen when I multiply them together. So I'm going to have a 3x in the middle. And this time I'm going to change the sign to plus. So that looks horrible. But basically it's x minus 3 times x squared plus 3x plus 9. And that would be the pattern. And the only thing that changes if you're looking at a sum of cubes is the signs. So for example, if I had x cubed plus 27, then this becomes a positive and this becomes a negative. And again, I apologize, my board's acting up. So those are, that's how you would factor binomials. If you have a trinomial, that's where you want to look at the product of your a times c and find numbers that multiply to give you that and add to give you your b term. So let's go ahead and take a look at these expressions. So in parts A and B, you're just going to be reducing those fractions. And it's tempting, it's very, very tempting for students to start canceling right here. So students might notice that 16 goes into 64, and so they might try to start canceling here. But I'm not allowed to do that because of this addition. It's not the same thing. If I were multiplying, that would be fine, but because it's addition, I can't cancel. So the first thing I want to do is factor. So if I look at this top expression, the first thing I'm looking for is a common denominator, or a common factor, and in that case it would be 4. So if I undistribute the 4, I'll be left with x plus 4, because 4 goes into 4x x times, and it goes into 16 4 times. In the denominator, notice that I've got a binomial. There's nothing in common, and I'm dealing with x to the 3rd, which is my clue that I'm dealing with a perfect cube. So I got to think about 64 as a perfect cube. And when I do, I realize the cube root of that is going to be 4. The cube root of x cubed is x. So if I'm thinking about my first set of parentheses, I'm going to follow this sign, and it'll be x plus 4. And then when I'm dealing with cubes, the next thing is a trinomial. And I'm going to square both those numbers. So I'm going to have an x squared here and a 16 here. The number in the middle is the product. So this is going to be a 4x. The first and third term are always positive. The middle term is always going to be the opposite sign that I started with. So it's going to be minus. And then I'm going to look to see if there's anything that I can cancel. And in this case, the x plus 4 quantities are the same. So I'll be left with 4 over x squared minus 4x plus 16. Let's take a look at letter B. Again, in my numerator, I want to see if there's anything in common that I can factor out. Well, 7 goes into itself, and I know 7 goes into 49 7 times. I also have an x in both of those expressions, so I can factor out a 7x. So I'm dividing it out. When I divide it out of the first expression, I'm still going to have an x left. When I divide it out of the second expression, I'm just going to have 7. So I'm going to have x minus 7 on top. In the bottom, in the denominator, I've got a trinomial. So this is where I want to think about numbers that multiply to give me negative 28 and add to give me negative 3. And some students are able to do this right away. Others need to do a little bit of trial and error. So for example, I might look at the product of, 1 times 28, or maybe I'm looking at 2 times 14. 3 doesn't go in evenly, but 4 goes in there 7 times. And I might keep going through until I figure out all of the different pairs of numbers that will multiply to give me 28. I also have to recognize that 28 is a negative number. So if I'm looking at the product, one of those two factors has to be negative. And I want the bigger number to be negative so that when I add them together, my sum is negative. So if I think about that, this would be what I'd be looking for. Well, 1 plus negative 28 is going to give me a negative 27. 2 plus a negative 14 is a negative 12. 4 plus a negative 7 is going to give me a negative 3, and that's what I'm interested in. So the pair of numbers that is going to help me factor this expression are the 4 and the negative 7. And since this is an x squared, when I break it up into factors, this is going to have to be an x, and this is going to have to be an x, so that when I distribute it back out, I get the x squared. And then it doesn't matter where I put the plus 4 and the minus 7. But I do notice once I do this that I do have factors in common that will cancel. And I'll be left with a 7x over x plus 4. All right, let's take a look at number 8. 8 has 4 different problems in it. And the rules for multiplication, division, addition, and subtraction are all kind of different. I think students usually struggle with addition and subtraction the most because in order to combine the fractions, you have to have a common denominator. That's not the case with multiplication and division. But with multiplication and division, you do need to factor everything so that you can simplify the expressions with cancellation. The other thing with division is that you want to change it to a multiplication problem. And you'll notice that in part B and C, we're expressing division in 2 different ways. Let's go ahead and take a look at A. A is just straight up multiplication. But as it's written, there's nothing that I can do to simplify. I can't cancel anything right as it's written. So what I want to do is factor each of these expressions so that I can look at it in terms of a way that can be canceled. So again, with this expression here, that's I think the same expression that we factored in letter B above. So I know this first fraction, I'm going to have an x minus 7 and an x plus 4. Underneath, my x squared minus 49, so there's nothing in common that I can pull out. So I am looking at a binomial, and both of those numbers are perfect squares. So if you remember, we can follow our difference of squares formula. So if I've got x squared minus another perfect square, if I take the square root of both of those expressions, I can look at I can look at the sum and the difference and multiply them together. So if I think about the square root of x squared is just going to be x. So I'm going to have an x plus and an x minus. The square root of 49 is 7. Okay? And then I'm going to multiply. I can't really do anything with that 4 in the numerator. But in the denominator, I notice that there's a 4 in common because 4 goes into 4x. It also goes into 16 4 times. Okay. Now that I've got it written like this, I want to look for things in common. I can see that the x minus 7s are going to cancel, and the x plus 4s are going to cancel. I also see that I have a common 4 that can cancel as well. Notice that everything in the numerator is gone. It didn't disappear, though. Some students have a tendency to say, okay, so x plus 7 is my answer. The thing is, x plus 7 is left in your denominator. So you have to have something above it to make this still work. And so when I cancel everything with multiplication, I'm left with a factor of 1. So my final answer would be 1 over x plus 7. In letter B, this is really intimidating because you have this like double fraction. But just remember, when I'm writing an expression as a fraction, I'm just dividing. So I want to think about this instead as 5x squared over 18 divided by 25x over 6. And the rule for dividing is simply to change it into multiplying by the reciprocal. So if I think of it that way, the first expression stays the same, but the next one becomes multiplication, and I'm going to flip or take the reciprocal of the second fraction. Just like if I'm subtracting something, so if I have 3 minus 7, for example, that's the same thing as adding a negative 7. It's the same thing as adding the opposite. So with multiplication and division, they're also inverses of each other. So at this time, I want to see if there's anything in common that I can cancel. And there's nothing really obvious, except when I think about my 6 and the 18, both of those numbers are divisible by 6. 6 goes into itself one time, and it goes into 18 3 times. The 5 and the 25. 5 goes into itself one time, 5 goes into 25 5 times. I also notice that I've got factors of x on top and the bottom. Since I only have one factor of x on the bottom, that will cancel, but I'm still going to be left with one factor of x on top. So in this case, if I multiply across what's left, I still have an x in my numerator, and in the denominator, I want to figure out what 3 times 5 is. And that's going to leave me with 15. Letter C, this is another division problem, and one where I'm going to want to multiply by the reciprocal. So if we have 8x plus 32 over 10x, I want to think of this as a multiplication problem. So I'm going to flip or take the reciprocal of that second fraction. And again, I want to factor everything. So if I look at the first numerator, 8x plus 32, I recognize that 8 goes into 32 4 times. So I can factor that out. 8 is going to go into 8x x times, and it's going to go into 32 4 times. My denominator is going to stay 10x. There's not much I can do with that. And then in the second fraction, the 2 will stay in the numerator, but that denominator, again, is the difference of squares pattern. X squared and 16 are both perfect squares. The square root of x squared is x. The square root of 16 is 4. So I'm going to have an x minus 4 and an x plus 4 as the factors. And then again, because everything is now written as multiplication, anything in the numerator can cancel with anything in the denominator. So my x plus 4 quantities will cancel. And I can see that 2 goes into 10 evenly. 2 goes into itself one time, and it goes into 10 5 times. So if I think about what's left in my numerator, I just have an 8. And in my denominator, I'm going to have a 5 times, actually I have an x in there too. I have a 5x times x minus 4. Okay. When we get to letter D, I can see in this case I'm adding two fractions. Well, if I'm adding, I must have the same denominator. So if I were to add, for example, let's say I had 2/3 and I wanted to add that to, I don't know, 1/5. So I have to figure out what my common denominator would be. And what I mean by that is, what is a number that both 3 and 5 divide into evenly? So my lowest common denominator is going to be 15. And then I want to think about, how can I transform both of those expressions so that they have a denominator of 15? Well, if I think about it, 3 goes into 15 5 times. So this fraction, in order for me to get the denominator, I'd have, whoops, let me fix that, 2/3. All right, so in order to get that first fraction to have a denominator of 15, I would need to multiply the denominator by 5. And that'll give me 15 in my denominator, but it would also change the value of my fraction. So to keep it balanced, I'm going to multiply the numerator by 5 as well. And that way, because if you think about it, 5 divided by 5 is just 1. So even though I'm going to change the way this fraction looks, I'm not changing its value. The second fraction, in order to get my denominator to be equal to 15, I'm going to need to multiply the denominator by 3. And again, to keep it balanced, I'll multiply the numerator by 3 also. So then when I rewrite these fractions, this first fraction is going to become 10/15. And then I'm going to add it to this fraction, which is now going to be 3/15. And when I put them together, I get 13/15. So this process that I did with numbers, I'm going to now translate to my rational expressions. So even though you have an x plus 1 and an x minus 5 in the denominator, if I think of them as factors, my common denominator in this case is going to be the quantity x plus 1 times the quantity x minus 5. So that's what I want my new denominator to look like. So if I think about that first fraction, it's the x minus 5 that's missing. So I'm going to multiply the top, the numerator, and the denominator by x minus 5. In the second fraction, it's the x plus 1 that's missing. So that's what I'm going to multiply by the top and the bottom. Because as long as I do that, I'm still just multiplying by 1. So let me just re-express what I have here. In the first quantity now, let me do this with a different pen. So now if I'm just looking at this first example, I'm looking at 2x times x minus 5. And that's going to be over x minus 5 times x plus 2. And I want to add that to 1 times x plus 1. And now that is also going to be over x minus 5 times x plus 2. Now I'm going to go ahead and simplify my numerators. So if I distribute my 2x here, that's going to leave me with 2x squared minus 10x. I can now add them, right? So I'm going to do plus, if I distribute my 1, that's going to give me an x plus 1. Since I have the same denominator now, I can put that whole thing over the x minus 5 times the x plus 2. And then my last step is just to see if there's any more I can simplify. And since my numerator has 2 single factors of x, I can put them together. So I'll have 2x squared minus 9x plus 1 over x minus 5 times x plus 2. And then you do want to just give it a check to see if there is any way to factor the numerator. And because I have a trinomial, I'd be looking at the product of a times c, which would be 2 times 1, and a sum of negative 9. So I'd be looking to see, are there any numbers that multiply to give me 2 and add to give me negative 9? And there aren't. So my numerator is what we would say is prime. And that would be my final answer. All right. In the next set of problems, you are solving equations. And solving equations actually is, I think, a little bit easier than adding or subtracting and multiplying and dividing, especially in the first 3 examples where you have one fraction is equal to another fraction. This is your basic proportion. You guys learned how to do this in middle school. If you've got 2 proportions that are equal to each other, so for example, if I have x over 3 is equal to 5 over 6, I'm just going to cross multiply to solve. So I'd have 6x equals 15, and then if I divide both sides by 6, I'm going to get x equals, and that's going to actually reduce to, what, 5 halves? We can do the same thing with rational expressions, where we have x in the denominator. So as long as I have 2 fractions that are equal to each other, I can cross multiply. So just make sure that you think of these as quantities, though, so that you're actually distributing through a quantity. So if I cross multiply, I'm going to start with a 4. So I'll have 4 times the quantity x plus 3 on one side. And on the other side of my equal sign, I'd have 2 times the quantity x minus 1. The next step would be to distribute and simplify. So this is going to leave me with 4x plus 12. On the right-hand side, I'll have 2x minus 2. Now, I can see that this is a linear equation because my x is not raised to any power. And I've got everything on a single line, so I know that this is a linear equation. So if it's at all possible, I want to gather my x's on one side of the equal sign and my numbers on the other. So what I'm going to do is go ahead and subtract the 2x from both sides. And at the same time, I'm going to go ahead, because I want to move the 12 over here, so I'm going to subtract the 12 from the left-hand side. So when I do that, I'm going to get a 2x. My 12's cancel on the left. On the right-hand side, my x's cancel, and I'll be left with negative 14. And so the last step would simply be to divide by 2, and I get that x is equal to negative 7. And again, when you're solving an equation, you do want to look to see, you do want to check for extraneous solutions. And again, remember we said with the even root functions, the extraneous solutions occur in functions that have a restricted domain. And because a rational function, we have those vertical asymptotes, it's possible that when you solve an equation, you get a value for x that's not in the domain. So if I go back to the original problem, I can see the denominators in this equation are x minus 1 and x plus 3. So I got to think about what numbers would cause the denominator to be 0. So that would be, in this case, if x equals 1, or in this case, if x is equal to negative 3. Both of those values would cause a 0 in my denominator, and my function wouldn't exist. So one of the things I would maybe want to say is that x cannot equal 1 or negative 3. And as long as my solution isn't one of those numbers, then I'm set. So I can go ahead and say the solution to this equation is x equals negative 7. Let's take a look at letter B. Let's start off by restricting the domain. In this case, if I look at that first fraction, I know that x cannot be 2. If I look at the second one, I know that x can also not be 4. So when I go to solve, I want to make sure that my answer isn't one of those 2 numbers. Because if it is, it's not really a solution at all. It's an extraneous value. So in solving this equation, I'm going to do the same thing. I've got one fraction equal to another, so I can go ahead and cross multiply. So I'm going to start with my x times x minus 4, and that's going to equal 3 times x minus 2. We'll go ahead and simplify. So that gives me x squared minus 4x. Notice now I've got an x squared term, so this is quadratic. So the next step is going to be a little bit different than it was before because I might have to factor to solve. So when I distribute here, we've got a 3x minus 6. And again, since this is quadratic, there's no way for me to get x by itself because I have a factor. I have an expression that involves an x squared, and I have an expression that involves a single factor of x. So there's no way to isolate either one of them without having an x on the other side. So in this situation, I want to group everything on one side so that I have 0 on the other. So I'm going to be subtracting 3x from both sides. And I also want to add the 6. Okay, so when I simplify, I'm going to have x squared minus 7x plus 6, and on the other side, everything cancels, so I'll have that 0. I'm left with a trinomial. So I want to think about numbers that multiply to give me 6 and add to give me negative 7. And so if I think about the numbers that multiply to give me 6, it's 1 and 6 and 2 and 3. I know that because my product is positive, either both of these numbers need to be positive or they both have to be negative. Since the sum is negative, I know that both of those numbers have to be negative. And so the two numbers that will add to give me the negative 7 are the negative 1 and the negative 6. So I'm going to go ahead and factor x minus 1 times x minus 6 is equal to 0. And then because I'm multiplying two things and my answer is 0, I know that one of those quantities has to be 0. So either x minus 1 is equal to 0 or x minus 6 is equal to 0. We did this back in our quadratic unit. So either x is 1 or x is 6. And I'm going to just go back and check my domain here, because my domain is basically that x can't be 2 or 4. And because neither one of these numbers are 2 or 4, I've got two solutions to this equation. But let's take a look at letter C. It looks very, very similar to the first two. I'm going to cross multiply again. Actually, let's talk about what the domain is. Since I've got an x plus 5 in the denominator, I know my domain is that x cannot equal a negative 5. That's going to be my vertical asymptote. So let's go ahead and cross multiply. I'm going to get x times x plus 5 is equal to 4 times x plus 5. I'm going to go ahead and distribute. So I get x squared plus 5x is equal to 4x plus 20. And again, I've got something quadratic, so I'm going to move all my terms to one side. It's important when you're dealing with quadratics that the x squared term is positive if you're trying to factor it. So I'm going to subtract 4x from both sides and the 20. So I'll have x squared plus x minus 20 is equal to 0. Everything cancels. So I'm looking for numbers that multiply to give me negative 20 and add to give me 1. So if I think about all the numbers that multiply to give me 20, it's 1 times 20, 2 times 10, 4 times 5, and I think that's all of them. Since I'm multiplying to get a negative number, one of those numbers has to be negative. But if the sum is positive, I want to make sure that it's the smaller number that's negative. And so if I think about those numbers, negative 1 plus 20 is 19, negative 2 plus 10 is 8, and negative 4 plus 5 is 1. So that's the pair that I want. So I've got x minus 4 times x plus 5 are my factors, and that's got to equal 0. And again, I'm just going to use my 0 product property. If I'm multiplying two things and I get 0, then one of those quantities has to be 0. That's the only way that'll happen. There's no way that I can multiply two numbers that aren't 0 and end up with 0 as my product. If I add 4, I'm going to get that x is 4, or that x is negative 5. But remember, we said at the beginning of the problem that x can't be negative 5 because it would leave us with a 0 in the denominator, and that's not allowed. So this is extraneous. The only solution that works would be the x equals 4. Okay. The last type of equation that we looked at would be when we're looking at the sum of rational equation, or if I'm adding two rational expressions and setting it equal to another. So in this situation, because I have more than one rational expression on each side of the equal sign, I can't use the cross-multiplying process to solve. So in this case, since I'm adding two rational expressions, well, I'm adding 1 over x minus 8 to a 1, in order for me to add those together, I would need a common denominator. What makes this nice is that if I multiply both sides by the common denominator, all of the denominators will end up canceling. And another thing that's nice about this one is that the common denominator is pretty obvious. It's just going to be x minus 8. And so if I distribute that expression to the first fraction, the x minus 8s are going to cancel. So I'm just going to be left with 1. If I think about distributing it to the 1, it's not going to have anything to cancel with, so it's just going to be 1 times the quantity x minus 8, or just x minus 8, but I also have to remember to distribute it to the other side. And since my denominator has an x minus 8 in it, it's going to cancel with this x minus 8, so I'm just going to be left with a 7. So this ends up being pretty nice. I'm going to go ahead and simplify the left-hand side, and I get x minus 7 is equal to 7. And if I add 7 to both sides, I get that x is equal to 14. And then the only other thing I want to double check is to make sure that it's in the domain, which I probably should do at the very beginning. And if I take a look, both of these fractions have a denominator of x minus 8. That means that the only thing that x isn't allowed to be is 8. And in this case, 14 is an 8, so I know that my solution is not extraneous. Okay, the last two problems we have to do are applications of rational functions. So let's take a look at number 10. It says, Miss McNeely and her friends want to rent a beach house in Florida for a week in June. Airfare costs $225 per person, so each person is going to have to pay $225 for themselves. The beach house costs $1,200, so we're all going to split that. The total cost of the trip, and that would be airfare and the house, are going to be divided evenly among the people who go on the trip. So if I don't know how many people are going, I'm going to call that x. So x represents the number of people going on the trip, and y would be the average cost for each person. And remember, we're going to be splitting the whole thing. So if I wanted to write an equation for that, so we're looking for the average cost. Well, let's think about the total cost first. We know that the house is going to cost $1,200. That's a flat fee. But that each person is going to have to pay $225 for their airfare. So I've got to think, that's going to be $225 times the number of people that are going on the trip, which we're calling x. Then I'm going to take that total amount, whatever it is, and I'm going to split it among all of the people that are going. Again, that's just my x. So there's the equation that represents the average cost per person, or the average cost per trip, if you wanted to think about it that way. And so in letter B, it's saying, well, what about if 6 people go on the trip? What's the average cost per person? So the thing that you have to pay attention to here is, where is that 6 going to go? Is it going to go in for x, or is it going to go in for y? So pay attention to how your variables are defined. If x represents the number of people going, then I know I'm going to let x equal 6. That means that y is going to be 1,200 plus 225 times x. Oops, I don't want to put an x there anymore, right? We know it's 6 people. So I'm going to go ahead and plug the 6 in here. And then I also want to divide by 6. So let me pull up my calculator, because this is where students sometimes make mistakes when they're entering it in. I've got to think about the quantity in my numerator as a whole quantity. And so when I enter it into my calculator, you can either enter it twice. So I can enter the numerator, press enter, and then divide by 6, or I can enter it all at once. If I enter it all at once, though, I have to remember to put parentheses around the entire numerator. So I'm going to take my 1,200 plus the $225 that each of the 6 people is going to be paying. I'm going to end my parentheses, because that's a total that I want to divide by the 6 people that are going. And when I do that, I find that it's going to cost us $425 per person. And remember, this is a word problem, so keep everything in context. The average cost is going to be $425 per person. Let's take a look at letter C. If Ms. McNeely wants to keep the cost at no more than $300 per person, obviously if it's going to cost $425 for 6 people to go, and I want to make the cost smaller, remember that inverse relationship, right? If these two quantities are inversely related, if I want the price to decrease, that means the number of people going is going to have to increase. So I want to figure that out. So this time, I'm given the y value. So I'm going to go back to my original equation, and I'm going to replace the y with 300. I don't know x anymore. I'm trying to find a different value for x. Well, this just goes back to what we were doing solving equations, where I've got a fraction equal to a whole number. Well, if I put that whole number over 1, now I've got 2 fractions equal to each other, and I can use my process of cross-multiplying. So I'm going to have 300x is equal to, well, I don't really need to multiply the numerator by 1. That's just going to be 1,200 plus 225x. And so this is linear now, so I can go ahead and subtract the negative 225, or subtract 225x, to get my x's on the left-hand side, that's going to leave me with 75x equals $1,200. And so if I take my 1,200 and I divide by 75, that's going to mean that 16 people have to go on this trip. It better be a big house, right? All right. Let's take a look at the last problem. So it says the function c of t, which is equal to 5t divided by 0.01 t squared plus 3.3, describes the concentration of a drug in the bloodstream over time. In this case, the medication was taken orally. Not that that matters to the math. C is measured in micrograms per milliliter, and T is measured in minutes. The maximum concentration in the body is 13.76 micrograms. After how many minutes does this occur? So in this case, you have to solve an equation, and so if I know the value of the concentration, I've got to think about, is that going to be my variable C or my variable T? And C, we are told, represents the concentration. So I'm going to replace this quantity here, that C of T, with a 13.76, and I'm going to rewrite my equation. So I've got 5T over 0.01 T squared plus 3.3. Now, this is a problem that I think would probably be better suited to use the calculator. We could certainly cross-multiply here, but just seeing this coefficient in front of the t squared, I can see that I'm going to be dealing with something that's quadratic, and having that as my coefficient is going to make it difficult to factor. So we could use the quadratic formula, but if this were on the calculator section of the test, it's going to be easier for you just to go ahead and solve this graphically. So what I would do in this case is I would create a system of equations where I'd have one equation, so I'm going to split it up. So I'm going to have one equation equal to the left-hand side. So y1 I'm going to set equal to 13.76. And then the second equation, or the right-hand side, I'm going to create another equation. On the calculator, I'm going to go into y equals. If there's anything there, I'm going to clear it out. I also noticed that you can see how my plot 1 is darkened and highlighted. That means it's turned on. So if I just put my cursor up there and press enter, it'll turn it off. Okay, so I'm going to go ahead and enter the 13.76 in for my y value. And then for the second equation, I want to do my 5t. Now notice that when I use my variable button, it comes up as x. That's fine. So it's going to be 5x, and then I'm dividing by this whole quantity. And it's really important when you put this in the calculator that you put it in parentheses. So it's going to be 0.01. It's going to end up being x squared plus 3.3, and then close your parentheses. So it's going to be divided by, in parentheses, 0.01 times x squared plus 3.3. Okay, and I'm going to go ahead and graph it. And I usually start on a standard window. So if I go to zoom, I'm going to choose zoom 6. A standard window goes from -10 to +10 on both the x and the y axis. Okay. And when I do that, I see a graph. I don't know which one it is, but actually I do. If I think about this first one, since it's just y equals a number, this is going to be a horizontal line. And I can't even see it. So what I'm seeing must be my y2. Okay, but I can't see where they intersect. I mean, obviously, I'm looking to see where they intersect, and I can't see it. So I've got to figure out some way to adjust my graph. Certainly, you can jump to zoom and notice that you have a zoom out option. So if you zoom out and press enter, you can do that. And when I do that, I can see that my two graphs do intersect. So if I want to find that point of intersection, I'm going to go to second, and then notice above the trace button, there's something that says calc. If I hit second and then trace, I have this menu of options, and I want to choose intersect. And then I just need to tell my calculator where the point of intersection is. Now, it's possible that there could be multiple points of intersection. Since I'm dealing with a real quantity here, I probably don't want my time to be negative. So if the graphs did happen to cross on, say, like the left side of my coordinate plane, the answer probably wouldn't make a lot of sense if I ended up with negative time. So I'm going to choose the point that is in my quadrant 1, because that's going to make the most sense for both time and concentration. I would expect them both to be positive. If you move your cursor close to the point of interest and then start pressing enter, the calculator will prompt you to pick the first and the second curve. If you only have two curves graphed, then it does it automatically. It asks you to guess, but then press enter one more time, and it'll give you the point of intersection. And so that point of intersection has an ordered pair. So we've got the ordered pair 17.8. Let's go ahead and say 0.86, and then the y value is the 13.76. Well, let's think about it. On our calculator, we're talking about x and y, but in this equation, our x is really time. So here's the time, and our y value is the concentration. So this is the concentration, and this is what we knew, right? We set the concentration at 13.76. We were asked how many minutes or after what time does this occur. So the answer to my question, and I'm probably going to want to refer back to using the t, is going to be t equals 17.86, and the units of interest were minutes. Okay. So again, this is on the calculator section. So when you're given a situation and you've got all these decimals, not to say that you couldn't do it algebraically, but it does help if you have the calculator to just use technology to find that point of intersection. So we've done it a couple different ways. You've done it algebraically, and now we've done it on the calculator. Well, I hope this helps. Good luck on your exam. Good luck.